My name is Cavin Ward-Caviness. It's my pleasure to come here and speak before you. It's really been an amazing meeting. I hope everybody's taken away as much from it as I have for it, and it's always a difficult task to follow up so many incredible speakers, so I'll just try and hold your attention for a few minutes and hopefully tell you a little bit about some of the ways that we're trying to connect between aging or molecular aging, as I like to say, social stressors and air pollution for it, and blend together a little bit of epidemiology and toxicology along the way. So I always start off my talk, and this slide can almost be skipped, but where you live matters for it. This is from a study done in Los Angeles County back in 2015 for it. They decided to map the life expectancy across the Los Angeles County basin for there. And while the overall county had very high life expectancy, they found very nearby neighborhoods that had extreme differences in life expectancy here. For it. On the outline in black, you have Walnut Park, with life expectancy over 90 years, and just about a 10-15-minute walk to the east of it, you have Cudahy City, with life expectancy just under 80 years for it. Now, these are both primarily Hispanic neighborhoods, both lower income, both lower SES for that. And so when I saw this picture, I was like, well, there must be something environmental here going on. It's not explained by crime for it. Crime differences aren't that big over these small scales for there. It's certainly not explained by demographics or SES for there. And so my mind goes to, what is it that confers amongst one neighborhood such a long life expectancy and another, such a shortened one. And we can see this, across the United States. You take any major city, you do the similar mapping, you'll find that. And you'll find the greatest disparities oftentimes between minority communities and non-minority communities for it, or between historically discriminated communities and those who have not experienced such discrimination. And so I think it's our charge, and the charge has been laid before us over the course of this meeting, really to understand these and to take these lessons learned and really turn them into actions, as we've heard many times. So a lot of my work centers on how aging and the environment intersect for it. And over the past several years, due to the development of several biomarkers of aging, particularly using DNA methylation, we've really been able to scientifically interrogate the aging process in ways we have not been able to in the past for it. And through this, we've learned that adverse environmental exposures, both chemical and social, are associated with several outcomes that are associated with aging for that, mortality, CVD, cancer, but also associated with the aging process itself. Considering the environment as a modifier of this intrinsic aging process, I think can be a means to understand environmental health risks in a way that we have not before for that. If you think about, sort of shortened life expectancy that we see amongst, a lot of communities, a lot of that can be tied into a concept of aging for there. Now, within the concept of this talk, I'm not going to be able to give you a full conceptual definition of aging. Suffice to say that there are many out there for it, and I think the environment can have a role to play in any way in which you define that. And I believe that molecular aging biomarkers and novel study designs are going to be a key to understanding this and to making this tangible. So there have been several studies, I'm giving you just a selection of them, that have indicated that the environment, can alter, biological age or is associated with altered biological age, whether that's a causal factor or not for that. And that includes exposures like long-term exposure to air pollution and even the neighborhood environment and social cohesion for there. We've heard some talks about, the importance of social cohesion throughout there, and it turns out that social cohesion, in fact, might be intrinsically important for how you age and how you develop, not just in your early years, but also in adulthood. This is a photo I'd like to sort of talk about what do we consider to be aging for it, and who do we consider to be aged for this. This is one of the world record holders for the oldest living individual for it. He died back in 2015 for it, and this is sort of a timeline of his life. And I like to hold this up here to say, this is a person who's exceptionally long-lived for there. Died at age 112 for it, but he did not have a stable life. He lived through 2 world wars for there, was born in Japan, so lived through a famine after the Second World War for it. For there, and probably had a host of other sort of complicating adverse exposures in there, particularly given, the country he lived in and the times that he lived in for it. And so I asked the question of, is this person, how did he get to be so old? Is this a resilient aging where there's certain lifestyle factors that he had, where there are genetic factors that he had that made it so that he lived much longer than others in an environment that probably produced people who were, died earlier than expected, given the, long-lived nature typically of a lot of Japanese individuals for it? Or are there other factors, for that? Did he just happen to have a beneficial environment? Did he luck out in some way for that? And how can we understand that? How can we connect what allowed him to live well beyond 100 and transfer that to other individuals? Now, this is another aspect of aging that we have here. Virile young man in 2009 that I'm sure many of us recognize for it. And in 2016, much, much older. Now, I'll say as president of the United States, he had access to the best healthcare in the world for it. There was absolutely no treatment that would have been barred to him within there. Now, on the converse of that, he certainly had exposure to a lot of stress, job stress, not social stress in the concept that we might be using it when talking about economically disadvantaged neighborhoods, but some aspects of the mental stress, factor in there. And so how does that contribute to what we might consider an acceleration of the aging process over a relatively short time frame for that? And, how do we use that to understand how different stressors impact us and age us in different ways? I consider aging to be a fairly central aspect of how the environment interacts with clinical disease, heart disease, neurological disorders, and others in there. What this diagram here sort of represents, and I've seen others try to use the pointer, and it works on my hand, but not quite on the screen There we go for it. So you have environmental exposures which can directly impact, obviously, health and disease for it in ways that are probably completely independent of any intrinsic aging process for it. But you also have environmental stressors that I believe, I think others in the field have well shown now, that can potentially modify the aging process within there. Now we typically measure the aging process now through either physiological biomarkers for there. So these might be things like increased inflammatory markers for it. You can measure metabolic biomarkers and be like, okay, you're a little physiologically older than others. And we also have molecular biomarkers, things like DNA methylation or the transcription of genes can also give us a clue as to how you're aging. Now, I put this as a bidirectional error because we still yet don't fully understand the degree to which aging sort of directly modifies these markers, and these markers might be a readout of aging. So maybe how your epigenome changes is just simply a readout of other processes that we have yet to discover and measure for that. And there also might be a relationship where you might be able to change some of these intrinsic molecular biomarkers, and there's no shortage of billionaires starting companies now to try and modify their aging process for it. And in that way, sort of changing your molecular state, you might be able to change your biologic age. Now your chronological age is fixed. That's going to go by 1 year for as long as you're on this earth for it. But your biological age, that certainly might be reversible for it. And I think there's early evidence to suggest that at the very least, it is modifiable by environmental and behavioral factors for that. And then of course you have the relationship between the environment and the molecular biomarkers and disease itself that might be independent of the aging process. So this is a very complicated picture for it, and I can tell you, without going into too much detail, that epidemiologists and others don't like bidirectional arrows in these graphs. It really mess up modeling for it, and you've really got to bring in a host of other fields of study to try and understand things when things could go both directions, and sometimes at the same time as well, certainly on the time scales that we measure them. But that doesn't make the picture any less true for it. And so I believe that no matter how much we might dislike the fact that yes, factor A can modify factor B and vice versa, we need to recognize that and utilize it to the degree possible. So over the course of the next sort of few minutes or so, I'm going to go through sort of 3 points or 3 aspects of the research program that I've developed over several years. One's going to look at epigenetic aging and neighborhood disadvantage, trying to understand how the neighborhood environment might modify the aging process. Then we're going to talk about a newer model that we're developing to try and look at sort of housing stress within an animal model and how that modifies aging within mice. They're giving us a different causal look at the aging process and molecular biomarkers. And finally look at aging as a sensitivity factor for future environmental exposures. And I don't see anybody keeping me on time, so somebody's going to have to wave from the crowd if I go over. So first, I've talked a bit about epigenetic aging, but I haven't actually described sort of what it is for there. And so epigenetic aging is a means for determining the biological age of a tissue using DNA methylation, typically Illumina arrays. Now we're moving into whole genomes or bisulfite sequencing for it. As I showed, on some papers before, this has been linked with environmental exposures and health risks, and thus might be able to explain the associations we see between the environment and particularly chronic disease or developmental disease. The nice thing about epigenetic aging is, A, it's biologic, so we're not focused on chronological age, which is non-biological but still very useful in some prediction equations, and also it differs for every cell type and every tissue within your body for there. And so your epigenetic age of, say, your eye might be very different than your skin. And this is actually, going to be different based on the different physiologic disruptions you have, going on in different tissues. And so we can actually look at tissue-specific disease using some of these biomarkers and understand how what these biomarkers tell us about cardiovascular disease through aging of the heart for it, or tell us about what it tells about through metabolic disease through aging of the liver for there. And there's some early stage studies going on in that, and I'll come back to that point when I talk about our animal model, because that's exactly what we hope to do, is start to build multi-tissue phenotypes of aging, associate those with environmental exposures, and use that to understand how the environment affects different tissues in different ways and what that means for the overall health of the organism and eventually the population. Within this study that I'm going to present to you, we use 3 epigenetic aging biomarkers for there. There's a whole constellation of them that are out there, and there's new ones developed every week. Each one has sort of a slightly different purpose and a slightly different interpretation, which complicates things, but I like to leverage that to understand what common story are they telling me, and what are the differences between the stories that these biomarkers tell me, and how do I leverage those to understand how the environment might be differentially affecting the aging process. I said we looked at the neighborhood environment. What I actually mean by that is, so we looked at 19 different indicators of the external environment in which these people live. This study was done in Detroit, Michigan for it. It was actually fairly unique for an epidemiologic study at the very least, because we actually had trained assessors go out to every neighborhood in Detroit and look at the different features of that neighborhood for there and report back for it. So we actually had a fairly systematic map of the neighborhoods in Detroit and at least their built environmental features for it. And we used a mathematical technique known as principal components analysis, which you've heard a little bit about in yesterday's talks for there, to sort of collapse these and get an overall score of what the environment means. And we actually got 9 different scores representing sort of 9 different sort of principal components or features of the environment that combined our 19 different indicators into a single vector there. And what we found is that the neighborhood environment is significantly associated with epigenetic aging biomarkers for it. So on our y-axis here, we have the effect estimate. So this is accelerated aging in years. So if you go up, this means 1 year of accelerated aging, 2, 3, 4. You go down, this is sort of decelerated aging for there. And on our x-axis, we have the different principal components. You can think of these as different features of the environment that we have here. And what we found is that there was one, principal component 7, that was associated with all 3 of our epigenetic aging biomarkers, so quite consistently associated with them, and quite substantially associated as well for this. So this is on a standard deviation scale here. So a standard deviation increase in this is associated with about 2 years of accelerated aging, within these neighborhoods for there, which is a not insignificant amount, especially when considering the association between accelerated aging and mortality that are reported in other studies. When we looked at what was sort of responsible for this principal component 7, we found things like abandoned cars, people on the street, graffiti within there, and the street being in poor condition for it. And so this sort of reflects some of the disinvestment that happened. So this study was done just after the financial crisis in Detroit, and those of you who sort of live, in or around that area sort of understand the population displacement that happened, people leaving the city quite en masse after the collapse of the auto industry in large part for that, and some of the disinvestment that happened in a lot of these cities. And we believe this is a reflection of that particular signal and showing that it might be accelerating the aging of these individuals. What we didn't see, what we did publish in the paper, was that we also had measures of how people felt about their neighborhoods for it. So, did you like your neighborhood? Do you feel like your neighborhood is socially cohesive for it? And this signal is actually independent of those. So independent of how you feel about your neighborhood, which did have a different impact on aging, the neighborhood built environment itself still could be, through some proxy factor, accelerating the aging process. Now, it wasn't an entirely negative story that we found. So we also looked at beneficial environmental features, and that's the fact of the question, do you see the same associations if you have beneficial environmental features such as green space? And what we found is that green space seems to exert a protective effect. So if you're in these neighborhoods that seem to be accelerating aging, if you also have the presence of green space, particularly large mature trees, for that we seem to see a protective effect there. We don't see those same associations that we observed initially for it, suggesting that green space might be a buffer against this, and there's a lot of research now that's going into social cohesion and other beneficial factors being able to be a buffer against adverse environmental exposures, and we think this is one of those signals that's going to come out of there. Now, we did that study, and that's all well and good, but that was an association study, cross-sectional, a lot of assumptions made in there, and not a lot of causality that we can say about it for there. And so, over the years afterwards, I and others, at the Environmental Protection Agency had this idea to take a mouse model that had been built up over the years to understand how housing stress impacts mice's response to wildfire smoke and other air quality exposures like that, and say, okay, well, are these mice actually aging differently? And is that partially responsible for the differences in the response to wildfire smoke that we've seen within there? And so we set up a study using 144 mice, and we had a depleted housing environment. So think of it like a bear cage with sort of nothing, in there, no running wheel, nothing to play with, nothing to hide within there, things that, mice like to do. We have the enriched housing environment. So this comes with a running wheel for there. This comes with some little stuff they can play with within there. They've got a little hut that they can go in and hide in, which mice particularly enjoy doing. It seems to be a psychological benefit for them for that. And we had mice that stayed in one environment the entire time, so over a 24-week period for it. We had mice that switched environments, so went from enriched to depleted housing and depleted housing to enriched housing. Now, obviously, this is a study that we could never do in human populations. We could not just simply force somebody to move from a penthouse and, kick them out, and send them out on the streets. And it would be obviously highly unethical to take somebody from, depleted housing environment, move them up to a nice housing environment, and be like, okay, eventually we're going to move you back. We're just going to watch and see what happens in the meantime. And this is where sort of those different study designs really come in importance, because they allow us to causally interrogate some of these factors that we could not do in human population studies. And this is early stage data, so this is literally just sent to me a week ago, and I sort of stuck it into the presentation for there, but I think the story that it's telling is really interesting and really compelling for it. So we have our sort of 4 conditions here. So we have mice that stayed in depleted housing for the entire time period. I'm starting us at week 12 here. We actually, started doing some measures at week 4. We have mice that started in depleting and moved to enriched housing at week 12. So week 12 was a switchover for it. Stayed in enriched housing the entire time, went from enriched to depleted housing. You can see at 12 weeks, so these mice have now been in their housing environments for 12 weeks. For our enriched housing, mice have a lower body fat percentage, which is the measure that I'm using here. I'm not using this because I think it's the most relevant measure for understanding health or metabolic health in general. It was the measure that had the most striking graphs for it, and I'll talk about some of the other ones later. But we can see that these mice certainly have a lower body fat percentage, for our enriched versus depleted housing, which we sort of expected. What's interesting is that just 6 weeks after a switch for it, mice that went from depleted housing to enriched housing have moved way down in their body fat percentage relative to the mice that have stayed in depleted housing. And that gets even more extreme as you go to 24 weeks out for that. The converse of that story is mice that went from enriched to depleted housing sort of went up a little bit relative to the mice that stayed in enriched housing for there. And you go to 24 weeks and that story gets even more extreme for it. And we're certainly seeing that this housing environment has a strong effect on these mice, at least in their metabolic health. And we believe that this is a possible, what we call in vivo model of health span, or at least metabolic health span for that. In that, what we noticed overall in the data is that at week 4, depleted housing mice had more fat, had a higher fasting plasma glucose, more cholesterol, and more LDL cholesterol than mice that were in depleted housing. And mice that were enriched housing. And mice that were in enriched housing would not reach similar levels over their age lifespan until about 18 to 24 weeks later in that. And so these mice that are in enriched housing seem to be able to maintain a better metabolic health over their time frame. And then the reversal seems to start to reverse those trends within there, and that after the reversal, you start to see the mice that were in enriched housing that moved to depleted housing start to see that health benefit go away over time for that. We're doing a host of other measures within this, including some molecular measurements, as well as to more fully understand that, and then connect this to the second part of the story that I'm about to launch into, which is how in the world does social stressors seem to make people more responsive to chemical environmental exposures. This connection between your social environment and your chemical environment that's proven to be quite robust, quite strong, and I believe to be quite important as it's emerged in the literature over the past decade or so. So as I said, our next steps for the housing model is to build a multi-tissue model of this. So we actually collected multiple tissues. We collected brain, liver, adipose tissue, muscle, a few others that I'm forgetting right now, blood in there as well. We're going to map actually the multi-omic changes that we see in these mice over this time span and connect those to different sensitivity factors to understand what is protective about the housing. We also want to look at which components of the enriched housing are responsible for the observed effect. Is this all just a physical activity biomarker that we're looking at here? And if we took away the running wheel, might the enriched housing not be enriched anymore for them? And conversely, can we look at that in human populations? People who have access to walkable neighborhoods, people who have access to local parks and other features that can allow them to do physical activity and report on using those facilities. Do we see similar effects as what we see in our mice for it? And we want to, as I said, understand if these changes in these biomarkers can be used to understand environmental sensitivity, as that's been a story that's been emerging over the past several years. The fact that your social environment might be sensitizing individuals to chemical environmental exposures that they receive later on in life. And so the final part of my story, that's what I'm going to talk about for it, which is the question of does accelerated aging, particularly accelerated aging biomarkers that we saw were associated with the social environment, modify associations with air pollution. For the first part of the story, I'm going to go back to our tried and true cross-sectional studies for there. This is using 500 participants located at, who were seen at Duke University, and we looked at multiple aging biomarkers and asked if they modified responses, modified associations between traffic-related air pollution and cardiovascular responses that we had previously seen within this cohort. These are some of the maps of the exposures that we see. They look pretty typical, as you might expect. This is sort of the urban core. This is sort of the urban core of these neighborhoods. We see the high levels of diesel and gasoline, particulate matter within there, as well as secondary organic carbon. Different responses for biomass. We didn't really study biomass, but I wanted to make sure that our models looked like we sort of expected. Biomass related air pollution more towards the rural areas, traffic related air pollution more towards the urban core for it. And what we saw is that these positive beta interactions here indicate to us that individuals who had higher accelerated aging, as measured by these different aging biomarkers here, had increased risk of peripheral arterial disease, increased diastolic blood pressure, increased systolic blood pressure when exposed to traffic-related air pollution as people who had lower accelerated aging. We can look at this graphically as well for it. On our y-axis here, we have the odds ratio, so the odds of having peripheral arterial disease in there. So increased odds means increased health risk for there. This is looking at the association between proximity to traffic and peripheral arterial disease. And our 2 points here, these are our slow agers, as I call them. So these are people who are like the slowest agers within our cohort, and these are people who are aging the fastest. And you see the people who are aging the fastest had clearly the highest health risk for it. And there are actually no health risks for it, or no association between traffic-related air pollution and peripheral arterial disease, which is a very robust association. We've seen this half a dozen times within these studies. So seeing no association really suggests that there might be a fairly strong protective effect of lowering the aging process for it. And the fact that these aging biomarkers are driven pretty strongly by the social environment, to me suggests that there might be a pathway to modifying the aging process for individuals living in stressful environments by improving their environmental condition, lowering their accelerated aging, and thus protecting them against future chemical environmental exposures. Was a really unique link between the social and the chemical environment. Now, as I said, that was an observational study, so we asked ourselves, well, could we do this in a causal study design for it? If we actually controlled the exposures that individuals were receiving for it, could we also see similar things? So we went back to a study that was done at our EPA facilities where they expose individuals to low-dose ozone for 2 hours for it, so not a traffic exposure, but gets us both another environmental exposure to make our study more robust and a causal study design for it. Our N was only 17 because these studies are very expensive, so you can't get hundreds of individuals through them, but it does give us a really unique look at aging and causal associations between air pollution and different physiologic markers. And what we observed there is what we observed before for it. So our x-axis here is age acceleration for it. Going from left to right is increasing, more accelerated aging. The values are negative, but that's because of the way we modeled aging acceleration within this particular cohort. The other unique feature about this is these are all very young individuals. So these are people that are in their 20s for it. And so what this graphic suggests is that for even people that are relatively young, small differences in aging can be very strongly responsible for how they respond to the environment. So the y-axis here is the response that we saw of C-reactive protein to ozone. The y-axis here is the response of the QT interval, which measures the depolarization, the repolarization of the heart. Longer QT interval bad. Generally, we think increased C-reactive protein, increased inflammation bad. My thought here is that this is actually reflecting the immediate positive inflammatory response to ozone that's being depressed in people who have accelerated aging for it. Conversely, we see that people who have accelerated aging seem to have longer QT intervals, suggesting a worsened cardiovascular response to short-term ozone exposure. We can look at this even more. We had a statistician from Harvard, Maria Bell-Ben, brilliant causal modeler from Harvard University, work with us on a novel methodology that we're now publishing for it. And what we see graphically, we also see when we apply causal methodology, suggesting that people who have accelerated aging and accelerated aging using biomarkers that are modified by their social environment for it seem to have worse responses to environmental exposures, both traffic and ozone related. So in conclusion, I would say that environmental exposures seem to be intricately linked to the aging process. For that. That includes both on the clinical side, which has been well studied, but also we're seeing it on the molecular side now, which I think is very novel and very influential. Housing-related stress, I believe, may influence metabolic health span. And that's a study that we're going to be really expanding on over the next several months and years, hopefully. And beneficial environmental features may be able to at least buffer against some of these effects. So it's not just a wholly negative story. There might be things that can be done by altering green space and other beneficial environmental factors for it. And finally, I believe that molecular biomarkers may indeed be a tool for understanding the molecular basis behind how different environmental justice-related factors get underneath the skin and modify the responses of individuals to future chemical environmental stressors that we know they're more likely to experience because of the intersectionality of the social and the chemical environment, particularly for those who are adversely exposed to both. And so with that, I'd like to acknowledge the many contributors to the study, and I'd be happy to take any questions with the time remaining.